going to talk about what does the restriction really looks like in GGP problem. Thank you. Welcome.
This is better. Yes. All right. So thank you for coming to this to the talk in the morning. Let me begin by thanking the organizers of this conference to have invited me to give this talk. This is a bit of a survey talk, surveying some recent developments on branching problems in which I have played some role over the years. But I think the talk that I am giving today is based on more recent developments. Before I begin on this topic, maybe I should say that the lecture is basically trying to understand, given a representation pi of a group G, and suppose you have a subgroup H contained in G. The question is, how does pi restricted to H decompose as a representation of H? So if one was dealing with finite dimensional complex representations of finite groups, then there is no subtlety to the question, although the precise answers may not be so easy to obtain. So I want to give one or two examples to begin the talk. Suppose G is equal to Sn and H is equal to Sn minus 1. Then one knows that irreducible representations of the symmetric group Sn are parametrized by Young tableau of size n. And then so say that to a tableau lambda, we have the representation pi lambda of the symmetric group Sn. Then one of the interesting branching laws is that this pi lambda from Sn, when you restrict to Sn minus 1, it is direct sum of pi mu, where mu denotes Young tableaus of size n minus 1, which are contained in Young tableau of size n, which means that the representation restricted to Sn minus 1 is the direct sum of those representations whose Young tableaus are obtained from the ambient Young tableau by removing one of the boxes and still keeping it a Young tableau. So this is one of the classical branching laws, as they are called. It describes the decomposition, and maybe I will do one more. This is called the Northern Freedom. it is about a tensor product of irreducible representations of U2 of irreducible representations of U2. And here one knows that every representation is of the form sim k of C2. And the theorem is that sim k tensor sim L of C2 is equal to sum of sim k minus L plus I greater than equal to 0. Maybe it is easier for me to say that it goes from this sim k minus L plus 2 dot 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 sim k plus L, where k is variable. So there is a, I feel I should remove this. Okay, yeah, better. So in, no, H2, it's better. Okay, all right. So in both these examples, one of the aspects which I want to bring out is that there is a nice decomposition, but it's a direct sum of irreducible representations. And what I'm going to discuss in my lecture today will be context in which such a simple-minded decomposition is not there, and still we want to understand some kind of a decomposition. Before I begin, this GP, so this G comma H will be called a GGP pair. So, so the groups involved are GLN plus 1, GLN, SON plus 1, SON, and UN plus 1, UN. And there are a few other derivatives of these groups, but we will not bother about them. Okay. So the branching laws for complex representations of group describe how a representation of a group decomposes when restricted to a subgroup, which in the case H is compact is a direct sum of irreducible representations. So this is what I was trying to illustrate in the context of finite or compact groups. When dealing with infinite dimensional representations of a real or a PRT group, G restricted to a non-compact subgroup H, the branching laws describe irreducible representations of H which arise as a quotient representation. So this is what is called the branching law. You try to understand which representations of the subgroup arise as a quotient of your representation of the bigger group. It is not clear if this allows one to describe how an irreducible representation of G restricted to H looks like. For example, the irreducible representation might appear as a subquotient of the representation of G in many ways. And this branching law, which only deals with quotient branching laws, will not be in a position to discuss which irreducible representations appear as a subquotients. The lecture is an attempt to discuss this question. Most of the lecture will deal only with periodic groups, though many of the notions and questions along the way will make good sense for real groups also. The lecture is will focus only on periodics, but many questions will make good sense for the real groups also. Okay. So assuming G to be a reductive group, restricting an irreducible smooth representation to H, we get a smooth representation of H which is rather large. So I think that is one aspect which one has to keep in mind. that these are not finite length representations. These are also not even finitely generated representations. One is dealing with rather large representation. This symmetry breaking, in which we further project to a particular Bernstein block of the category of smooth representations of H, has considerable degeneracy and might also be zero in certain blocks, meaning the restriction to H followed by projection to a particular Bernstein block erases most attributes of pi for the GGP pairs. So I already said that GGP pairs are these groups GLN plus 1 to GLN, GLN plus 1 GLN, SON plus 1 SON, UN plus 1 UN. This representation of H is a projective module for H for many blocks, though not for all blocks. After some preliminaries, the lecture reviews works principally due to Chan and Savin on this topic. At the moment, there are no results when the restriction of pi to a block is non-projective. So I just list a few of the questions which I thought about, and for which it looks interesting to give an answer. Some answers seem available, but not in great generality. So what is the support of pi restricted to H in the variety defined by the Bernstein center of that block? Is it a closed subvariety? When can it be a proper subvariety? What is the fiber of the set theoretic map from irreducible representations of H which appear as a quotient of pi to the Bernstein variety of that block? Okay, so this is how the branching laws are typically studied. And the first important result about branching laws considered in these pairs is the multiplicity 1 property, say for the pair SON plus 1 comma SON. And it says that this dimension of the Hom space pi 1 pi 2 is less than equal to 1. So this is also the case for these two branching. Restriction from Sn to Sn minus 1 decomposes as a sum of irreducible representations, and all of the ones which appear, they appear with multiplicity 1. And the same is true for the Clebsch-Gordon theorem. And in fact, multiplicity 1 theorems are typically, whenever they arise, they are quite useful. So the GGP pairs have this multiplicity 1 property. One might think that this is a very classical result known for long years, but no, it is a result which is there only from last about a decade or so. This result is due to Eisenberg, Gurevich, Raleigh, Schiffman in the non-Archimedean case, and by Binyong Sun and Chen Boju in the Archimedean case. So it may be mentioned that before the full multiplicity 1 theorem was proved, even finite dimensionality of the multiplicity space was not known. So, since we are dealing with infinite dimensional representation, the multiplicity spaces might be infinite dimensional. It might even be identically infinite, which were later answered in greater generality in the works of Sakellades and Venkatesh. For infinite dimensional representation, which is what we are mostly dealing with, there is also the possibility that the multiplicity could be identically 0 for some pi 1. Because we are trying to locate some irreducible quotient of it, and maybe pi 1 is too big to have a irreducible quotient. So to begin with, m pi 1, pi 2 could be identically infinite or identically 0. That possibility is there. Okay. With the multiplicity 1 theorems proved, one then goes on to prove a more precise description of the set of irreducible admissible representations pi 1 of SON plus 1 and pi 2 of SON, for which this branching happens. This is called the branching, and so this is what are called GGP conjectures, and they have been all mostly proved. Okay, so precise theorems about the Hom spaces have become available in a series of papers due to Walsperger and Moiglan was Perget for non-Archimedean orthogonal groups. These were followed by a series of papers by Bouja Plasi for unitary groups, both real and periodics. The case of real unitary groups getting settled by works of Bouja Plasi, Hongyu Ha, and Hangyu. All these works are for tempered representation or more generally representations which lie in a generic L packet. There are works due to Cheng Chen and Jilin Luo in the Archimedean case for orthogonal groups, as well as those of Kobayashi and Spey for orthogonal groups. Okay. So given in the interest in the Hom spaces, it is natural to consider the related Ext spaces. And in fact, homological algebra method suggests that the simplest answers are not for the individual spaces, but for the alternating sum of their dimensions. So this is called the Euler-Poincare characteristic of the pair of representations pi1, pi2, which is an alternating sum. These hopefully more manageable objects, certainly more flexible when coupled with vanishing of higher x when available, may give theorems about the Hom spaces. So this is the point of view which has been current for some time. We must add that before we can define the Euler-Poincare, one needs to prove that these are finite dimensional when pi1 and pi2 are finite length representations. And further, one needs to prove that the x are 0 for large I. So this is, of course, only under these conditions can you define the Euler-Poincare pairing. So the vanishing of x for large I is a well-known generality. For reductive periodic groups G considered here, it is known that x pi comma pi prime is 0 for any two smooth representation when I is greater than the split rank of the group. This is a standard application of the projective resolution of the trivial representation provided by the Brouhard-Ritz building associated to G. So this is a generality, and that says that beyond the split rank of the group, X groups are 0. For the proof of finite dimensionality of X, we note that unlike the Hom spaces, Hom pi1, pi2, where we will have no idea how to prove finite dimensionality if both pi1 and pi2 are cuspidal, because cuspidal representations are some kind of a black box. One doesn't know their internal structure as clearly. On the other hand, for x pi1, pi2, exactly this can be handled a priori for I greater than 0, as almost by the very definition of cuspidal representations, they are both projective and injective objects in the category of smooth representations. And a projective object remains projective on restriction to a closed subgroup. So if one is dealing with supercuspidal representation, x are 0, higher x are 0, and therefore finite dimensionality is not an issue. So the finite dimensionality one needs to then prove for principal series representation. So the finite dimensionality of X when both the representation are full principal series is achieved by an inductive argument both on N, which is this SON, and on the split rank of the levy from which the principal series arises. The resulting analysis needs the notion of a Bessel model, which is also a restriction problem involving a subgroup which has both reductive and unipotent parts. So there is that approach by direct definitions of the principal series and analyzing orbits and so on, and one can make a proof which also has some utility. However, there is a general finiteness theorem about X groups due to Eisenberg and Ethan Sayag. The approach via Bessel models which intervene when analyzing principal series representations has as a bonus explicit answers about Euler point characteristic in some cases, not in all, but in some cases there are. So I want to bring this definition to your attention. I believe this notion is of older origin, but I take them from papers of Eisenberg and Sayag. The notion of locally finitely generated representation. So I said these representations that we are dealing with are not typically finitely generated, but they are locally finitely generated, which is good enough for most purposes. So suppose G is a periodic group, pi is a smooth representation of G, then pi is said to be locally finitely generated if it satisfies one of the two equivalent conditions. For each compact open subgroup K of G, pi K is a finitely generated module over this K algebra. Or for each cuspidal datum M comma rho, M a Levy subgroup of G and rho a cuspidal representation of M, pi M rho the corresponding component of pi in the Bernstein decomposition of the category of smooth representation of G is a finitely generated G module. So what happens is that the category of the smooth representation is a direct product of the category of smaller of blocks, and its projection to each block is finitely generated. So the whole representation is large, but when you project it to a particular block, it is finitely generated, and that is all that matters for the questions at hand. So this is a very useful notion. And then with this notion, of course, you have to see good cases when this applies. And indeed, in the GGP cases, it applies. So for pi and irreducible admissible representation of GLN plus 1, the restriction of pi to GLN F is locally finite. And more generally, this is true for a spherical pair where finite multiplicity is known, such as all the GGP pairs. And then the restriction of an irreducible admissible representation of G to H is locally finite. So all the examples, all the cases that we will deal with in this lecture are locally finitely generated, and which is as good as finitely generated for our purposes. And indeed, the notion of finitely generated for this talk is of crucial importance. Okay, as a consequence of this theorem of Eisenberg-Sayag, the restriction is finitely generated in any Bernstein component. Hence, pi restricted to GLN has non-zero irreducible. Okay, so this is one of the direct applications, that pi restricted to GLNF has non-zero irreducible quotients by generalities, a statement which we said earlier we do not know how to prove for a general restriction problem. So being finitely generated, now it has plenty of irreducible quotients, or at least some. Okay, so the following corollary is an easy consequence of standard homological algebra, where we also use the fact that if a module is finitely generated over a Noetherian ring, which need not be commutative, then it has a resolution by finitely generated projective modules. And the corollary is that pi 1 and pi 2 are admissible representations where finite multiplicity is known, such as in GGP pair, then X are finite dimensional and 0 beyond the split rank of H. Good. Okay, so I want to briefly tell you some of the branching laws which have been known or well known for some time, and then talk about their corresponding X analogs, and then talk about what I have been thinking about in more recent times. So, so this is a theorem which gets the subject going somehow, which says that an irreducible generic representation of GLN plus 1 and an irreducible generic representation given these two, the Hom space is always one-dimensional. It is non-zero and one-dimensional. So in some sense, when you restrict a representation pi1 from GLN plus 1, everything appears and everything appears with multiplicity 1. So this is what the statement was, one of the statement in the introduction was that when you restrict a representation in the GGP pairs from the bigger group to the smaller group, it loses most of its character. When you restrict pi1 to GLN, it is as if it is direct sum of all irreducible representation with multiplicity 1. But somewhere else, we may get some reflection of role of pi1. Okay. So the following theorem can be considered as the Euler-Poincaré version of the above theorem. And the point of the next theorem about Euler-Poincaré is that it is much more flexible than the previous theorem and also proved much more easily. And the theorem says that if you take, for this theorem, these representations are irreducible and generic, and both of them are irreducible and generic, and it is very important that they are irreducible and generic. Otherwise, neither multiplicity 1 is true and neither multiplicity non-zero is true. So both the statements go wrong. On the other hand, for Euler-Poincaré, you don't need to assume anything. The Euler-Poincaré statement is admissible of finite length, both for GLN plus 1 and GLN, and then X spaces are finite dimensional, and Euler-Poincaré is the dimension of the Whittaker space for pi1 times dimension of the Whittaker space for pi2. So there is one simple formula which works in all generality. So, given this theorem and given the earlier theorem about generic representation, it needs no big intuition to feel that two theorems must be related because of some vanishing of X groups. Okay, before I say that, there is this corollary which is curious. For irreducible admissible representations, the only values taken by the Euler-Poincaré is 0 and 1. In particular, it is always greater than equal to 0. Okay. So this is just a word about the proof of that theorem about Euler-Poincaré, and it uses some Bernstein-Jelvinsky filtration and Frobenius reciprocity, and then eventually it uses this fact about Euler-Poincaré on the same group, GLD, that if you have two finite length representation, then Euler-Poincaré is 0. If D is positive and if D is 0, then of course the Euler-Poincaré is dimension D times dimension W, and somehow basically this is how the theorem about Euler-Poincaré works. Good, I must keep a track of the time. Yeah. The following result conjectured by the author some years ago was recently proved by Chan and Savin for the general linear groups and by Rui Chen for all classical groups. This vanishing is at the root of why the simple and general result on Euler-Poincaré translates into a simple result about Hom spaces. That's for GLN and for, okay. So the theorem of Chan-Savin is that the X spaces are 0 for all higher I's if one is dealing with generic representations. Generic on bigger group, generic on the smaller group, then the X spaces are 0. And same statement for classical groups, and that is by Ryu Chen. That says that statements about Euler-Poincaré can be translated to statements about Hom spaces. Okay. Yeah. Sorry. This one, this is only for generic. The classical groups. No, the classical groups, the theorem about Euler-Poincare is not as simple as that one. For generic, the statement is not as simple as product of the dimension of the Whittaker spaces. So the higher x are 0, so Euler-Poincare is equal to the dimension, but Euler-Poincare is not product of the Whittaker spaces. Yeah. Okay, so this theorem about Euler-Poincare has also vanishing. So, we use theorem 3 and the previous theorem about Hom spaces to suggest vanishing of X groups. But it also allows you to prove that some X groups must be also non-zero. Because one knows that there are irreducible generic representations of, let's say, GL3, which have trivial representation of GL2F as a quotient. Similarly, there are irreducible non-generic representation which have irreducible generic representation as a quotient. For such pairs, the Euler-Poincare is 0 because it's product of the Whittaker spaces. So this is 0, whereas the Hom space is non-zero, and therefore for such pairs, X are non-zero. So the statement about Euler-Poincare allows you to prove that in several cases, X spaces can be non-zero. Okay, so here is a summary of known results about GLN. Let pi 1 be an irreducible admissible representation of GLN plus 1, pi 2 of GLN. Then we know that if both are generic, then this is one-dimensional. If both are generic, then X spaces are 0. And if both are parabolically induced from unitary space modules of Levy subgroups, these are representations of what are called Arthur type. These are the representations which appear in the residual spectrum. And they are the ones which are of interest for automorphic representations. Then there is a precise recipe of GGP called relevance, which says that the Hom space is non-zero if and only if these have a relevant pair of parameters. So these are A parameters, and there is some notion of relevance of A parameters introduced in our works. So this was conjectured a few years ago, and this has been proved by Chan and by Gurevich in the non-Archimedean case. But as far as I know, the case of Archimedean fields is open even for GLN. Chan and Gurevich have proved this for GLN, and this is open for GLN-R, GLN-C. Our conjectures was also for classical groups. The case of classical groups is open both in Archimedean and non-Archimedean cases. The work of Kobayashi and Spey on branching of orthogonal groups does not assume temperedness of representation and needs to be compared. So this I have not done and they have not done. They have only some branchings and one needs to compare their work with our proposal. Okay, so for certain representation, the branching laws are quite nice for GLN, and there is a recipe for classical groups. On the other hand, one could also ask if pi 1 and pi 2 are arbitrary pair of irreducible representation. There is a recent unpublished paper of Chan about when the Hom space may be non-zero, but at the moment the recipe is not easy to interpret or to use. So there is some generalities. about when this may be non-zero, but doesn't look that easy to use. On the other hand, even when pi1 and pi2 are products of space modules on discrete series, there is no understanding at present of when X spaces are non-zero. So as I said that Hom spaces are non-zero, there is a recipe which allows you to easily interpret if the Hom space is zero or non-zero for certain non-tempered representations. But for X spaces, this seems still open. Okay. So now I move on to somewhat of a different take on the previous matter. So far we have been discussing the question which representations of GLN appear as a quotient of an irreducible representation of GLN plus 1. Is it possible to have a more complete understanding of what a representation of GLN plus 1 restricted to GLNF looks like? The question is not so well posed, which we try to explain. Suppose R and S are rings, not necessarily commutative, together with a morphism S to R, which allows one to restrict modules for R to modules for S. We think of irreducible representations of groups as simple modules for rings. Thus, starting from a simple module M for R, we get a module for S through this mapping, and we call that module MS. The branching laws that we have been discussing are about simple quotients of MS as S modules. Thus, we are trying to understand Hom as S modules of MS comma N as well as this when N is a simple module for S. This is what our previous works have focused on to try to understand these Hom and X spaces for N a simple module for S. The question is whether that gives you a complete understanding of this object MS. I mean, in general, if a module, you know the co-circle, it's not clear how much it tells about the module. And this is what all the branching laws do. They understand, they try to understand the co-circle. Okay. So the first question that comes to mind is if for a finitely generated S module M, understanding these multiplicities for all irreducible modules, if all the multiplicities are known to be finite, determine the S module M up to isomorphism. So, here I have dropped that notation MS because now I'm not looking at relative situation S contained in R, but only S modules. And the only thing I take from restriction is that it is finitely generated. As I said, this is allowed. So we are not doing it in some great generality, but we are always in the GGP context, which captures a lot of branching problems, and therefore it's a reasonable thing to ask. Where based on low dimensional examples, I feel the question has an affirmative answer, though it seems not to have been investigated. Here is the precise question where we are using, without loss of generality, finitely generated representations instead of locally finitely generated representation. And the question is, let H be a reductive periodic group, M1, M2, to finitely generated representations with multiplicity 1, that is, the Hom spaces are at most one-dimensional for all irreducible representation of H. Then the question is that suppose these dimensions, which are less than equal to 1, are equal for all irreducible representations, then is M1 isomorphic to M2 as H modules? And the suggestion is that this is true for all GGP pairs. I'm not saying this for general reductive group. It is for modules M1 and M2, which are a restriction of representations of the bigger group to the smaller group. So the restriction problem, which has been studied in the literature over last few decades, indeed captures all the structure as a module for the subgroup. GLN plus 1 to GLN, SON plus 1 to SON, UN plus 1 to UN. Okay. Okay. So they are saying, okay, this is maybe a bit controversial statement I make here. There seems to be no general template for understanding modules over rings, commutative or otherwise. For example, I believe one does not have a classification of finitely generated modules, or even over the polynomial ring in two variables. So how then is one supposed to understand MS as an S module? You know, the question that we are trying to understand is that given a module for GLN plus 1, which is irreducible and therefore understood, you restrict it to GLN and you try to understand it as a module, not only through its irreducible quotients. Yeah, okay. Yeah. Uh-huh. Uh-huh. Yeah. And you, we are, you know, as I said, I am doing restriction problem from GL2 to GL1. I am not looking at modules as such. These are coming from irreducible modules of the bigger group. And one is saying that if all the branchings are the same, then the restriction of the representations pi 1, pi 2 to the subgroup is the same. And indeed, in the case of GL2 to GL1, GL2 has many representations, but it is a fact that all the representations restricted to GL1 are identical. They are, if it is cuspidal, then it is realized on the short space on F star by Kirillov theory. And in other cases, it has a, the short space of F star sits as a submodule of codimension 1 or 2. But the bigger module, because we are dealing with a PID with no torsion, those are also free modules. So this question certainly is good for GL2 to GL1. Okay. Yeah. So, so one is suggesting that although general modules may be hard to understand, it is possible that finitely generated projective modules over S have a simpler structure, which we may hope to understand. In fact, for the GGP questions, we are in the context of modules for which multiplicity is less than or equal to 1 for all simple modules. So there is this extra bit which is there. We call such modules multiplicity 1 modules for the ring S. And if MS is furthermore projective, it will be called projective multiplicity 1 projective module over S. And the question that I want to deal with is that, yeah, set here. So vanishing of X groups in many cases, but not in all cases, suggests that the restriction to GLN of an irreducible admissible generic representation of GLN plus 1 is close to being a projective module without being one in all cases. So somehow this is a bit imprecise statement. Is close to being projective module without being one in all cases, since the category of smooth representations of GLN decomposes into blocks parameterized by inertial equivalence classes M comma rho that I talked about. We can ask if the projection to the particular block pi projection is pi M rho is a projective module in that block. That's the more precise question. So, you are given a representation of the bigger group GLN plus 1. You restrict it to a representation of GLN, but then you can also decompose the category of representations of GLN in blocks. And in a particular block, you want to know whether it's a projective module or not. And this appears to be an important question to understand given an irreducible representation. When is this a projective module? So we have many theorems about vanishing and non-vanishing of X groups. And we have to use all that knowledge to come up with a proposal. Okay. So there is already some literature on this question for restriction problem from GLN plus 1 to GLN. Then we consider the simplest case of the more general GGP problems for classical groups, restricting ourselves to one of the simplest questions on the tensor product, which corresponds to the restriction problem from GL2 cross GL2 to the diagonal GL2, which was this problem for compact groups. So this problem from the GGP perspective corresponds to the restriction from SO4 to SO3. And SO4 has a split form and a non-split form, and also a compact form, and they can all be treated. Okay, so the following theorem is due to Chan and Savin. The restriction of an irreducible admissible representation is a projective module in a particular block if and only if it is generic and all irreducible quotients of pi in that particular Bernstein block are generic. So it should admit no non-generic quotient. Of course, by that theorem about Euler-Poincaré, if it admits a non-generic quotient, then Euler-Poincaré is 0. And if there is a Hom space, then there must be an X space. And therefore, anyway, one knows one implication of this theorem. It is the other implication which is their work. Furthermore, if pi 1 and pi 2 are any two irreducible representation whose restriction is projective in a particular Bernstein block, then pi 1 and pi 2 are isomorphic in that particular block. So this is what I meant by saying that pi 1 and pi 2 have lost their character, they have become same. Not only have the same irreducible quotient, but they are the same. Nothing is left. And then in this one, if you have a smooth projective module in the Iwahori block, such that the Hom spaces are less than equal to 1. So this is what I called multiplicity 1 projective module. Then pi has only these two options. It is compact induction from GLNO of the Steinberg of the finite group or of the trivial one. So these two have multiplicity 1, and being compactly induced from finite dimensional, these are projective modules. And these are the only two projective modules of multiplicity less than equal to 1 for GLN. After this theorem of Chan and Savin, the unfinished tasks are: given an irreducible generic representation, can we classify exactly the Bernstein blocks in which pi is not projective? Equivalent to saying when it is projective. More generally, if pi is an irreducible representation of GLN plus 1, which may or may not be generic, can one understand projective dimension of pi restricted to GLNF in a particular Bernstein block? So, the branching problem from GLN plus 1 to GLN seemed very simple-minded for generic representations. But now we are going into deeper waters by trying to understand the restriction in the sense of modules. Okay. Yeah. Okay. So there is a complete theorem of Chan which gives a classification of irreducible representation which restricted to GLN are projective, thus remain projective in all blocks. And the theorem says that an irreducible representation of GLN plus 1 is a projective representation if and only if either it is square integrable or this n plus 1 is an even integer and pi is product of cuspidal on GLD, which is the half the size of this group. This is for all blocks. So typically what happens is that for most of the blocks, it remains projective. On a few blocks, it degenerates. So my earlier question was, can we classify exactly the Bernstein blocks of GLN in which pi is not projective? This question is not answered by the next theorem. The next theorem answers when it is projective in all blocks. Okay, so from theorem 6 of Chan, it follows that just like cuspidal representation, discrete series representations are always projective representation when restricted to GLN. So, projective modules, I said, if you restrict a projective module from a group to a subgroup, it remains projective. That is simple Frobenius reciprocity, I believe. But to do that for discrete series is quite an effort. This seems like a general feature of all the GGP pairs, that a discrete series restricted to the subgroup is a projective representation, but there is no proof yet of this. Okay. So after all these discussions about restriction from GLN plus 1 to GLN, I want to discuss one classical group case in the case of tensor products. Following result about tensor product decomposition is much more complete than earlier theorems on restriction from GLN plus 1 to GLN. In this case, we are able to say not only when the tensor product is projective, but when not projective, we are able to say it is non-projective in exactly one Bernstein block, which we show. So the theorem is that if you have irreducible infinite dimensional representation, product of the central character is trivial, then the representation pi1 tensor pi2 of PGL2 is a projective module always, unless pi1 and pi2 are irreducible principal series of GL2, which is just this specific principal series, pi1 isomorphic to chi pi2 check. In which case it is not a projective module exactly in the block of PGL2F containing the character chi. Chi is a quadratic character. In particular, if at least one of pi1 or pi2 is a twist of the Steinberg, then pi1 tensor pi2 is a projective module in the category of representations. So in a generic sense, it appears that most restriction problems give rise to a projective module, but then there is also the question of which projective module. Okay, so by theorems of Chan-Savin, there are two projective modules of multiplicity 1 in the Iwahori block, which are these two, I said. In this case, the restriction problem from GLN plus 1 to GLN, if projective in the Iwahori block, picks up only this representation. There are only two representations possible, only two projective modules of multiplicity less than or equal to 1. And the restriction problem from GLN plus 1 to GLN, if it is projective, is picking up this. Um, on the other hand, there are 4 projective modules of multiplicity 1 in the Iwahori block of PGL2, which are these 4 modules. So these 2 are the same as what we encountered on the previous page. These 2, this and this, are Steinberg and trivial from the maximal compact. For PGL2, maximal compacts are there is not one conjugacy class, but 2 conjugacy classes of maximal compact. And we take these 2 from the last slide, so to say, and then there are 2 more, which are the other maximal compact in PGL2, where K is the normalizer of the Iwahori subgroup of PGL2, and epsilon is the order 2 character of K, which is trivial on the Iwahori, that is this. This is the trivial character. In this case, the restriction of an irreducible representation, if projective in the Iwahori block, can be any of the 4 projective modules. It may be noted that the 4 projective modules of multiplicity 1 in the Iwahori blocks are isomorphic outside the 2 unramified characters. So, these are 4 modules, but actually outside, after you localize away from a point, they are the same. So they are only different in a very minor way. Okay. So it would be nice to understand projective modules pi of a reductive periodic group which have multiplicity less than or equal to 1 as being the closest analog of rank 1 projective modules of commutative rings. Are there finitely many in any given block? Is there at least one in any block? Can one classify them in some ways? For the case of GLNF, theorems of Chan and Savin, there are exactly 2 such blocks. And perhaps these are the only 2 projective modules in the Iwahori block of any split, simply connected group with multiplicity less than or equal to 1, with an appropriate modification suggested by the case of PGL2 for split simple groups. The situation for general reductive groups is not clear. At least there is the well-known generality for simply connected groups that there is a compact open subgroup whose trivial representation appears with multiplicity at most 1 in any reducible smooth representation. Thus, the corresponding induced representation gives a project. So there is one always. These are called special compact subgroups which exist for all periodic groups. Okay. That's all. Thank you.
Thank you, Professor Prasad. Any question from audience?
So maybe you mentioned this, but when you say projective modules, are you working in the category of smooth representations or admissible representations, or the same?
In the admissible category, there are no projective modules.
In the GRN case, when you say that there are 2 multiplicity 1 projective module, isn't that you always consider only consider those which restrict from GRN plus 1 to GRN?
No, that is a absolute theorem. It is a theorem saying that there are 2 multiplicity less than or equal to 1 projective modules.
I see. Okay.
No restriction. No, it's not relative.
Other questions? Okay, if no, let's thank Professor.
That theorem is due to Chan and Savin.
Let's thank Professor Prasad again.